In this chapter, we will be discussing concepts in probability. In this lesson, we will be introducing some of the basic definitions that you need to know to understand probability.
Okay, so we're going to start by defining some ideas that are fundamental to the understanding of probability. So first of all, let's start off with a pretty straightforward one, probability. And you know that it's the likelihood that an event will occur, okay, the chance or prediction, okay? You're looking at an event, you're trying to figure out what is the likelihood that this specific event will occur here. So the probability of an event occurring is somewhere between 0 and 1, where 0 is definitely won't happen, and 1, the probability, if the probability is 1, that's yes, absolutely it will happen, okay? We usually write it as a decimal or as a fraction. When you write it as a percent, usually we call that chance, okay? The chance that something will happen is the percentage when probability is written as a percentage. Okay, and we understand probability to be when you're coming up with a ratio here, if you're looking at some sort of an event occurring, okay, the total number of ways that event can occur is in the denominator, and the number of favorable outcomes. So basically, you're looking for the probability of this specific event occurring. It's the number of ways that particular event could occur over the total number of ways that this little event could possibly occur. Okay. Now, we'll talk about that in a little bit more detail in just a second here, if that's not clear. There are two types of probability. There's theoretical, and then we've got experimental. Now, theoretical is when you look at some sort of a scenario here and you think about, well, okay, how should it occur? Okay? Okay, how should it happen? So, for example, when you're rolling a die here, the probability of getting an even number. Okay, well, how many even numbers are there on the die? Well, there's 2, 4, and 6. There's 3. There's 3 ways this particular event could occur, okay, out of 6 different events, which means reducing that fraction, there's a 1/2. The probability is 1/2, 1 out of 2, that I will get an even number. So there it is. That's what we're trying to describe here when we're talking about favorable events. So how many favorable events are there here? There's 3 out of the total number of events that could occur here, which are 6. So that's theoretical, okay? That's me looking at the scenario thinking, okay, well, this is the number of ways it could happen. This is the number of ways that the result that I'm looking for could happen. Compare that with experimental probability, which is actually based on repeating an experiment and looking at what actually happens. Okay, because sometimes you might be playing with a die that's weighted somewhat oddly, and so the result is that you are not getting the even number a half of the time. Okay, so this is theoretically what should happen. Experimental probability is what actually happens. So let's take a quick look here at an example. It says if you toss a coin 10 times and the heads come up 8 times, then the experimental probability is 8 out of 10. And you can reduce that to a smaller fraction there. Those can both be divided by 2, so you get 4/5. Now, when you flip a coin, theoretically, you know that you should be getting heads half of the time. Okay, there's 2 possible outcomes and there's 1 head, so 1 out of 2 here. But in this case, that's not what you're getting, so you would assume that something a little weird is happening with that particular coin. Okay, now a little bit more in terms of vocabulary. Outcomes, okay? All of the possible results of an experiment, okay? So we're looking at some sort of scenario. Let's go back to rolling the die, okay? Outcomes, how many possible outcomes are there when you're rolling a die? Well, there are 6. 6 different results that can occur if you're just rolling the die once. Now, if you're starting to pair up dice and whatever, you can make these outcomes a little bit more complicated, but that's really all we're talking about here is the number of ways that whatever experiment you're building up here could occur. An event, okay, the probability of an event happening, okay, well, an event is that specific outcome or set of outcomes that we are interested in, okay? So this is the set of outcomes. Okay, the set of outcomes we are interested in. So if the probability of that event is 1, then that means that is 100% going to happen. The probability of the event happening is 0. It's never going to happen. Up here, the event that we were looking for was the even number showing up on that die. Okay, that was the event, and it turned out that there was a probability of 1 over 2 out of 2 that was going to occur. All right, let's keep going down here. So the probability, in the probability, if event A occurs, okay, there's also the probability that event A will not occur. So this is sort of similar to some ideas that we would have looked at earlier in set theory. Okay, these become kind of complementary events here. So the probability of event A not occurring is the complement of event A. So the probability of event A not occurring is written as, and we would write that as the probability of event A not occurring. Put a bar on top. Now sometimes if we want to be kind of consistent with what you saw in set theory, we might put a little apostrophe there to indicate negation, but often we would put a bar on top. And so it's a little bit hard to see that. The probability that event A occurs plus the probability that event A doesn't occur should equal 1. Okay, in other words, think of it like this. If that refers to event A, this is not A. Together, those are being add up to the whole universe. And in this case, when we're talking about probabilities, the universe, the sum of everything in there is just going to be 1. Okay, 100%. Everything, 100% of everything that can occur will happen within that universe. So therefore, the complement of the probability of A is going to be 1 minus the probability that A occurs. Okay, so you just need to know that as well. The sample space is the set of all possible outcomes. Okay, so outcomes are the specific ways that the event could, or the experiment could play out. The events are the specific ones that we're interested in. The sample space refers to all of them together. Okay, and so sometimes we would use a tree diagram to illustrate that. So for example, we might, do something like this where we're going to flip a coin here and the coin could come out heads or tails. Let's say we're going to flip 2 coins. So here's one coin, and then here's the second coin. It could come out as a heads or a tail, and this could come out as a heads or a tail. And so we might use a tree diagram to illustrate our sample space. And our sample space is going to be the list of all the possible events. So you could get a heads and a heads, heads and a tails, tails and a head, tails and a tails. And so this part right here becomes our sample space. That's what they're referring to. Now hopefully that gives you a bit of a sense of some of the vocabulary that we're going to be using. Now we're just going to jump in and do some questions based on what we've just looked at.
List the sample space for each of the following scenarios and answer the questions that follow.
Okay, so we're going to identify the sample space. Now if you're throwing one die here, the sample space is just going to be the set of values. 1, 2, 3, 4, 5, 6. Those are all the possible results from rolling a single die here. If we're going to roll 2 dice, that's a little bit different here. And so we're using this table here. I could get, now if I start off with, let's start off horizontally here. So this is going to be 1 and 1. This would be 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6. 2 and 1, 2 and 2, 2 and 3, 2 and 4, 2 and 5, 2 and 6. Now I know this is going to be a little bit long. I'm going to try to do this as quick as possible here. 3 and 1, 3 and 2, 3 and 3, 3 and 4, 3 and 5, 3 and 6. 4 and 1, 4 and 2, 4 and 3, 4 and 4, 4 and 5, 4 and 6. 5 and 1, 5 and 2, 5 and 3, 5 and 4, 5 and 5, 5 and 6, and finally 6 and 1, 6 and 2, 6 and 3, 6 and 4, 6 and 5, and 6 and 6. Okay, there are 36 different ways you can roll 2 dice, okay, and get different outcomes here. So now, based on this right here, what's the probability of getting doubles? Okay, doubles. Well, first of all, there are 36 outcomes total. Doubles. The event is doubles, and now my favorable results here will be 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6. So there are 6 different ways that can occur, which means the probability of getting doubles reduces down to 1 out of 6. Okay? 2. What's the probability of getting a 2 and then a 3? Okay, well, we said that this was the starting one here. Now, so this assumes kind of that we're maybe rolling that one die there twice. Okay, and that's totally fine. There are still 36 ways that we can get we can roll the 2 dice here to get a 2 and then a 3, 2 and then a 3. Well, that's just this one outcome out of 36. How about the numbers add up to 9? Okay, well, again, there's 36 here total. Okay, add up to 9 here. Well, if they're going to add up to 9, I know that one of them can't be 1. Okay, I also know that one of them can't be 2, because with 2, the largest I could get here would be 8. I could do 3, though, because it could be 3 and 6, okay, or 6 and 3. So 3 and 6, 6 and 3. That would add up to 9. Okay, and then it turns out if you go along this diagonal, all of these add up to 9 here. 3 and 6, 4 and 5, 5 and 4, 6 and 3. So it turns out there are actually 4 of them there that'll do that. 4 out of 36. So there's a 1 out of 9 probability that will add up to 9, that the numbers will add up to 9. Now, that's just along this little diagonal here in my chart. Now, anything beyond that adds up to 10, there's 11, and there's 12 here. Okay, what's the probability that the numbers don't add up to 9? Okay, well, if 4 out of 36 add up to 9, then everything else won't add up to 9. So that means there's got to be 32 out of 36 that don't add up to 9, and that can be reduced, essentially that's going to be reduced to 8/9. Okay, kind of the exact opposite. And remember, when you add these guys together, you should be getting 1. Okay, the whole universe, when you add up complements here, the result should be 1. The probability that a sum of 3 or a sum of 4. Okay, sum of 3 or a sum of 4. Well, to get a sum of 3 would be 2 and 1 or 1 and 2. So there's 2 results there. Or a sum of 4. Well, 4 would be 3 and 1, 2 and 2, 1 and 3. So it could be 3, so there's 1, 2. Or 4, I'm going to add these up here, 1, 2, 3. So there's a total of 5 different ways to get a sum of 3 or 4. Now, just so that we know here, when you're doing that or here, that's going to be the sum of, so a sum of 3, so that probability plus the probability sum of 4. And we don't really run into any problems with that because there's no way you could get a sum of 3 and a sum of 4. There's no overlap here. So it turned out that was just 5 out of 36. And it actually turns out that doesn't even reduce. So that's as good as that's going to get. 5 out of 36. Okay? The probability that the sum of 3 and a sum of 4. Well, I just finished saying that you can't have those both together. It's not possible to get a sum of 3 and a sum of 4. So that is actually going to be 0 out of 36. Or just 0. Both are even numbers. Both are even numbers. Okay, let's come up to here. Well, if both are going to be even, then if one of them is 2, then I could get 2 and 2. So it's 1, 2, 3. So there's 3 ways here that could occur. 1, 2, 3. 3 ways here. And 3 ways here. So 3 and 3 and 3. So there's 9 ways total that could occur, that they're both even numbers. So that's 9 out of 36. And I'm just really counting that out. And when I reduce that, I get 1/4. So 1/4 of the time, both numbers will be even. Okay. Now the next one the next one here we're looking at one coin. What happens here when we flip one coin? Well, we're going to get either heads or tails as our sample space. That's pretty straightforward. If you've got 2, and actually I drew this one a little bit earlier here. If you've got 2, you could get heads and tails, heads or tails, and then heads or tails for that second coin, heads or tails for the second coin, depending on what happened here. So I'm either going to get heads and heads, okay, heads and tails, or it's going to be tails and heads, tails and tails. So there's my sample space, and I've got 4 different outcomes here. Here, what if a coin is tossed and a die is rolled? Okay, so if a coin is tossed, well then I'm going to get heads, tails, and then a die is rolled. Well, that's going to be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I'm regretting the fact that I drew it like that. But anyway, so my sample space here is going to be the set of, it could be a head and a 1, head and a 2, head and a 3, head and a 4, okay, head and a 5, head and a 6. Okay, it could be a tail and a 1, tail and a 2, tail and a 3, tail and a 4, tail and a 5, tail and a 6. And that's just me kind of summarizing the results at the end of each one of these little branches here. So now we're going to answer some questions here. You should recognize here there are 12 outcomes. So what's the probability of getting a head and a 2? Well, right there's 1 out of 12 different events. What's the probability of getting a head 3 or a tail and a 5? Well, there's no way that those can both happen simultaneously, so it's either going to be this or this one. I'm going to add those two probabilities together. Now, it turns out that's 1 out of 12, and that's 1 out of 12. So this is going to be 2 out of 12, or 1/6. What's the probability of getting the tails and an even number? Okay, tails and an even number. There's 1, 2, 3 different results in that event out of possible of 12. So there's reduces down to 1/4. Probably is 1/4 that would occur. And what's the probability of getting H and 7? Well, there is no 7. There's just no way that that's going to occur, so that's 0 out of 12 or just 0. Okay? And that's it. Kind of a big question there, a lot of different things going on here, but just some simple discussion about sample space, events, and probability.
A regular 6-sided die is rolled 50 times. The number 4 appears 10 times. Answer the following questions.
Okay, so this first question asks, what's the experimental probability of a 4? Okay, well, the experimental probability of a 4, we just got to look at it here. 4 appears 10 times out of 50. Well, the experimental probability of a 4 is 1/5. Now compare that with B that asks what the theoretical probability of getting a 4. Well, there's only 1 4 and there are 6 possible outcomes. So the actual theoretical probability of a 4 should be 1/6. Okay, that's what we would expect. This is what we're actually seeing. Now, in this case here, we only rolled it 50 times. That really may not be enough to get a nice demonstration of the distribution of the different values of when you're rolling a die here. But anyway, that's what we're seeing right now. Now, what's the complement of rolling a 4? Well, it depends. Is this going to be experimental? If it's experimental, then the complement, if its probability is 1/5, then its complement would be 4/5. But if we're talking theoretical, then the answer here should be 5/6. Right? Because the experimental probability was 1/5, so the opposite of that is 4/5. That's what's left over, and the theoretical probability was 1/6, and so its opposite would be 5/6.
A card is drawn from a well-shuffled deck of cards. What is the probability of the following?
Okay, so to understand what's going on with this, you got to understand that there are going to be 52 cards in a deck. There will be 13 hearts, 13 diamonds, 13 clubs, and 13 spades. Okay? And that in each one of these different suits, we call them suits here, there's going to be the numbers 1 to 10, okay, or ace to 10, and then there's going to be a card that's got a jack, a queen, and a king. 1 to 10, jack, queen, king. 1 to 10, jack, queen, king. They just have what we call face cards. There will be pictures on there. 1 to 10, and then jack, queen, king. So if you've never really played with a deck of cards before, you just got to have a little bit of an intro to that. So you're going to take a card out of the deck here. What's the probability that it's a heart? There are 13 out of 52 cards that are hearts, and that actually boils down to just 1/4. There's a 1 out of 4 probability that you're going to get a heart. Oh, sorry, I forgot black and red here. These cards here, these two suits are red, these two suits are black. Okay, so there are in the deck 26 out of the 52 cards that are black, which basically amounts to 1/2. There's a 1 out of 2 probability that you're going to pick a black card. The red 5. Okay, well, there are 2 red 5s. You could be talking about the heart or the diamond. Okay, so it turns out there are 2 out of 52, and that amounts to 1 out of 26 is the probability of getting a red 5. A red jack. Okay, well, that's the same sort of thing here. We're talking about a very specific card in those 2 suits here, and there are 2 suits, so there will be 2 out of 52. Okay, so or 1 out of 26. Now the probability of getting a face card. Now remember, the face cards are your Jack, Queen, King. There are 3 for each suit, which means there are 12 out of 52 that are going to be face cards. And why don't I do that again? What have I got here? That's 3 out of 13 when I simplify that probability. 3 cards. Basically, you're thinking about this. If you're talking about all the cards in a given suit here, 3 out of those 13 cards will be face cards. Not a face card, that's going to be the complement of this. Okay, and it's easier to think of the complement in this case right here. If 3 out of 13 are face cards, then 10 out of 13 won't be face cards.
A grade 11 class is to elect one of its students to be class representative. In the class there are 15 girls and 12 boys. The teacher is not allowed to vote. What is the probability that the person voted as a class representative will be one of the following?
Okay, well in this scenario here, I guess we're assuming that everybody's a potential candidate here, so what's the probability that it's going to be a girl? Well, it turns out there are 15 girls out of, based on what I'm seeing here, 27 students. Now there's a common factor of 3 to that, so that'll be 5/9. Probability that's going to be a girl. Now, the probability that'll be a boy is really the complement of that, 12 over 27, and again there's a common factor of 3 there. Take that out and you'll get 4/9, and then again you're seeing that those add up to 1 here. Now what's the probability that's going to be the teacher? Well, the answer is 0. Teacher's not allowed in that. Okay, we want a representative of the students. Okay, the teacher doesn't fit that condition. But over here, what's the probability that's going to be a grade 11 student? Well, there are 27 grade 11 students to choose from. We're going to choose one of those students. The probability is 1. Okay, it is definitely going to be a grade 11 student.
Given 10 cards. On each card, one of the numbers from 0 to 9 are printed. Each number is only used once. What is the probability of drawing the following?
All right, well, probably getting a 5. Well, there's only 1 5 out of those 10 cards. Okay, so the probability is going to be 1 out of 10. What's probably getting an even number? Okay, well, let's think about this. 0 now. 0 does count as even, so it's going to be 0, 2, 4, 8. Sorry, 0, 2, 4, 6, 8. Well, there's 5 of them. 5 out of 10, and that reduces to 1/2. Half of those cards are going to have even numbers on them. What about a number less than 10? Well, they're all less than 10. So there's 10 out of 10, or the probability of 1. How about a number greater than 10? Well, truth is, there are no numbers on there greater than 10. 9 is the largest that we get here. So then the answer is going to be 0. And actually, this is just following into that footsteps here. Don't get thrown off by the specific question here. The number 13, well, again, there is no 13 in that set of 10 cards. So again, the probability of getting a 13 is 0.
A box contains 36 red chips, 24 blue chips, and 40 green chips. If you take a chip from the box, what is the probability that it will be one of the following?
Okay, so the first thing you want to do here is figure out the total number of chips here. It turns out there's 100. And then what's the probability that you get a red chip? Well, there are 36 red chips there. And when you reduce that, those are both divisible by 4 here. You're going to get 9/25. So now what's the probability that it's not a red chip? Well, probably that's not a red chip. There's a 9 out of 25 probability that it is a red chip, right? If we simply subtract that, look at the exact opposite of that, turns out there are 16 out of 25 that would not be a red chip. Okay, just the complement of those two events here. How about what's the probability that it's not a green chip? Okay, well there are 40 green chips in there, which means out of the 100, there's got to be 60 that aren't green chips. So 60 out of 100. And so this reduces down here, with it be 6 out of 10 when you cancel 0 and then divide those by 2, so it's going to be 3 out of 5. Now, look at this last one here. Not a red chip or not a green chip. So probability that it's not red plus the probability that it's not green. Okay, because or, okay, remember, or means addition here in this context. So let's just take a look at what we get here. Well, not red we know was 16 out of 25, and not green was 3 out of 5. Let's add those all up there. Well, actually, we don't even, I was going to pull out the calculator, I don't really need to, because this is, I'm going to multiply top and bottom here by 5 to get a common denominator, so it'll be 15 out of 25. And when I add those together, I get 31 out of 25. That's more than 1. How is that even possible? Well, the truth is, if the set that you're looking for is not a red chip or not a green chip, well, what would happen if you pulled a red chip? Would that count? Well, yeah, because a red chip is not green. If you pulled a yellow chip, would that count? Yeah, so because it's not red or green. And if you pulled a green chip, would that count? Well, yes, because it's not red. Because remember, or only requires that you satisfy one of those two conditions, not necessarily both of them, just one of them here. So no matter what you pull out of there, okay, 100 out of those 100 chips will satisfy that scenario. So the probability is just 1 that that would occur.
A box contains 5 green pens, 3 blue pens, 8 black pens, and 4 red pens. A pen is picked at random. What is the probability that the pen is green?
Okay, so we're looking for the probability that the pen we grab here is green. Okay, well, 5 green, 3 blue, 8 black, 4 red. That's a total of 20 different pens there. So a pen is picked at random. What's the probability that it's green? Well, there are 5 green. So that means there is a 1 out of 4 probability that you're going to pick a green pen.
There are 28 students in Mr. Connolly's grade 12 mathematics class. The number of students in the yearbook club and the number of students on the student council are shown in the Venn diagram. Use the diagram to answer the following questions. What is the probability of being in one of these following sets?
Right now, we should recognize this question from this chapter on set theory. It's the exact same question. Now we're just going to add some probability questions to it. So first of all, notice there are supposed to be 28 people in this little universe here. There are 5 in this set, 2 in the overlap, and 1 in just this lone set here. So that's 8 people total, which means there are 20 people out here that don't fit in either one of those. So now let's just take a quick look here. What's the probability of being on the yearbook club and on student council? Okay, and that's the overlap between the two of them. Okay, so that's the probability, let's say yearbook and student council. There's 2 students there out of the 28. And that reduces to 1/14. What's the probability of being on only the student council? Only on student council only. Okay, doubling up on that. But this is basically student council and not yearbook. Just on student council. Okay, well, student council here, these 2 people are on both, so it's just that one person there. So 1 out of 28 people are on just student council. How about on the yearbook club? Oh, okay, well, that's just being in this circle right here. Now remember, there are 2 different subsets to this circle. There's 5 of them here, 2 of them there, so that's a total. So the probability of being on the yearbook, that's a total of 7 ways that can occur out of 28. And that leaves me with 1/4, a probability of 1/4 that you're on the yearbook club. On neither club, okay. Neither club. So that is going to be, now remember, being on one of those clubs, or at least one of those clubs, would be the union of those 2 sets. So we're looking for the opposite of that. So we're looking for a yearbook or student council, but not that. And it turns out outside there are 20 students. So 20 out of the 28. You can divide those both by 4 and we'll get 5/7. So the probability that you're not on either one of those clubs is 5/7.